tutorial, we're going to go through raster data and how we use this to create visualizations about continuous surfaces such as bathymetry or elevation. The first thing that we're going to do is download our data. So I've got 4 data sets that we need for this particular session. The first one is world-based map data, just to give us a bit of a reference of where things are, so we can just build visualizations. The next is Landsat. Here's some satellite data from the US GIS. We've got some bathymetry data, which we've got from the SRTM-30 dataset, which is the Shuttle Radar Topography mission, available from the Americans. And we've also got some species distribution data from one of my own studies. These files are rather large, so if you just give them a few minutes to download. I'll just start copying my data over so I can create my well-organized file structure. Remember, a good file structure will always help you organize your data and find it in the end. There's nothing worse than not being able to find what you're looking for. So, open a new blank map. What we're going to do first, and we're going to add in our world-based map data. There's 2 ways of doing this. First one is through our catalog. Remember to connect to your folder so that you can actually find it. And then we're just going to add the world-based map countries file in. We'll just double check, make sure that our coordinate system has been set to WGS 1994 or WKID 4326. So we've now got our base map. What we're going to do now is we're going to add in the bathymetric data. So if we have a quick look in the bathymetry folder that I created, you see here, SRTM-30 is shown with a little grid, a different icon to what we've seen before. However, if we go to Windows Explorer, you see that the file is actually very different. Whereas we got this here, we've actually got a folder. Inside it we've got these ADF files, some of which are quite large. This is the file format known as Esri Grid. So you need to make sure that you send all of these files along with that particular layer if you want to share it. It's one of those file formats that, a bit like shapefile, that comes with lots and lots of different ones. The OVR file is a pyramid. What it means is that as we zoom out, if the system has calculated larger pixels so that you will be able to zoom in and out very quickly without having to redraw the entire grid at every single zoom layer. So it's just a way of increasing the speed of visualization. It's always well worth, if the system ever asks you to build pyramids, because it will increase the viewing speed. It may take a little bit of time for them to calculate the pyramids, but it's well worth it. So this here, all of these files need to be sent along. That's what it looks like within our catalog. That's an Esri grid format. So what I'm going to do now is I'm just going to add in my grid. You can see it appears here, and we are underneath the world-based map layer. I'm just going to drag it onto the top so that we can see what's happening with it there. Zoom in. Immediately you see that this is a continuous data set. If I zoom in ever closer, we start to see the pixelization of the grid cells. So we can see the pixelization of the grid cells here. This is because it's a continuous grid of rows and columns. Each cell has a value. If it didn't have any value, it would have a number like minus 9,999, which would be a no value, and the computer would know that that contains no data, and it wouldn't show any data there. If we look at the table of contents, you'll see here that we've got a value high and low, so it's actually giving us the bounds of the data within the raster, so that we can build our visualizations around that. So we can do quite a lot with this data, but the first thing we're going to do is just simply change the color of the scale. And right now it's using a stretch scale going from white to black, as we can see in the table of contents. All you have to do is just double click on that color ramp, and we can select any color we want from the current options. You can add your own if you wish in future. I'm just going to select this blue one. Sometimes it will show the deeper values of the lighter color, for example, so we just click invert so that we have the deeper is darker and then elevation is lighter. And we can see some elevation Norway, for example, the Alps and so on, and around about the North Atlantic. We can see the different colours and the graduation. So that's one quick way of changing the coloration to increase the visibility of the data. Now for more control and more options, we would actually use the Symbology tab. So if you recall previous sessions where we manipulated the vector data, we utilized the properties, and then we have the Symbology tab, and it's exactly the same for the raster. So what we're going to do is right click on SRTM30, properties, and then we're going to go Symbology. And in here you can see that we've got a different set of show fields, but they're still fairly similar. We've got classified. We can start to classify our grid cell by various bits and pieces. We can change the color ramp, we can change the stretch type, we can use the hill shading effect just to illustrate some of the peaks and troughs a little bit. So we've got quite a lot of features that we can use in here. One of the more useful tools is classified, and it's a very quick way of just showing, for example, layers and contours or habitat types and things like that. It's just really about illustrating the patterns that you want to make visible. So we're just going to try classified. It asks you if you wish to compute a histogram, and yes you do. It will take a few seconds just to do that. And then here we're in a different window now, classified. We've got these groups with these bounds, and we can change the color ramp into whatever we want. Now I'm going to give you a task. What I want you to do is to classify using gaps of 1,000 meters elevation depth. So what we're going to do is using that. At the moment the classification method is natural breaks or jenks, and we can set the number of classes that we want. But we want to define that to be 1,000 meters to break. So we click classify button here. The method we change to defined interval, and then we change the interval size to be 1,000. And then click OK. And you see here we've got nice 1,000 meter bands now. Click OK. And there we go. We've classified our raster. You would use to classify if you had habitat types or sediment types, for example. It would be really easy to illustrate those different patterns. So one thing is that I've just got it the wrong way around here, is that my lighter shades are actually the deeper parts of the ocean, the darker shades are the highest points of the land. So I'm just going to go back in, and I'm just going to right click on my color ramp symbol here and click flip colors. So we'll just change it upside down, and then we've got something which makes a little bit more sense. Okay, so that's one way of changing the coloration of the layer, just to try and increase the visibility of certain bounds. But what if we're not really interested in the land? We only want the ocean data, which is a common case for most of us working in the ocean. What we need to do is remove any values above sea level from our dataset. And we can do that very quickly using a set no tool. So what we're going to do is click search button, set space no, enter. And we bring up the set no tool here, spatial analyst. So it's really simple. All we're going to do is the raster that we want that contains the values that we're going to test will be SRTM30. The input false raster value or constant value, which is where the value in the conditional raster does not meet the expression that we're going to code in a moment, will be given the value of either a constant value, for example 1, or the value of the raster cell which has been tested. So that's what we want. We want to preserve the depth data, but we want to remove the land data. The expression we're going to use, if you click the expression field, you'll see an example here. So we're just going to use that value, which is just the value of a grid cell. Greater than 0 will be set null. Any other value that does not meet that expression will be given the value of the original raster. We then find a location to store this. Remember, put it where you can find it. Without putting a file extension on, the computer will create a grid file, much like the original SRTM30. However, if we put TIFF on the end, it will create a TIFF image, which will work exactly the same way as a grid file would. Click Save and OK. We may have to wait for a minute because it's calculating, checking each individual cell to see if there's anything matching. And there we go, it's completed. And what you can see is we've got a set null layer here, and the top bound is -1, not 6,000 or 5,000. And we can see peeking through is the previous layer which is underneath it. So that's set in null. So we've just got a bathymetric layer now without any data poking through. No elevation data to confuse us. Okay? So this is great and you can use it for so many things, but on some occasions it's just too much detail and too much data. What we need to do is create some contours that just illustrate maybe 1,000 meters or 2,000 meter contour depth. So what we're going to do is we're going to use another tool now. And there's two ways to do it. The first way is to use the tool called Contour. And then you can use either 3D Analyst or Spatial Analyst. It doesn't matter which. They're both identical tools. The input raster will be our null raster. The output polyline feature will save contours underscore 1,000 meters dot shape. The interval that we're going to do will be 1,000 meters. The base contour, i.e. where do you start, 0. And the Z factor is 1. If you had data in feet, you'd change your Z value, for example. And it's just explained here within it. So you put 0.3048 if you had data in feet and you wanted to have a contour calculated correctly using a contour interval. It doesn't know what your data is in, doesn't know what unit is. So you will have to take that into account. So it's just 1 for the Z factor. Click OK. I'll just turn this layer off as we wait for the contours to be drawn. And there we go. Contours have been drawn in the shapefile. If we use the identify tool, it's a small blue circle with an eye in it, identify. We just click on the layer. And one of these contours we can see 2,000 meters. Click that one. 1,000 meters. 1,000 meters. A bit deeper. 3,000. 4,000. So we can see the contours in our visualization come out well. They really do illustrate the banks and slopes quite nicely. If we add on our layer again, we can see it's really illustrating those particular points in the ocean. That's one way of doing it. The other way, which is a quick way, which I don't really recommend, but if you were working on an area like this here and you wanted to illustrate some of these mounds quite quickly, maybe during a session where you're explaining some data to someone, you might just use a manual contour tool, and you just access that by right clicking in the toolbar area, going down to find the Spatial Analyst toolbar. Click that and it brings up the Spatial Analyst toolbar. Make sure that it says the name of the layer that you want to work on in that drop down, which is the null one. Then I'm just going to use this create contour button. And you can see my cursor has changed. If I could click on the map, I can just illustrate some features. And he just draws a contour for me. So you can do finely grained contours. Now, there's no data associated with this contour that you've just drawn. It's just a line, a graphic. And yet, we don't have any data. So you need to use the black select elements arrow. Just go over, right click. You want to delete it. Just press delete button and get rid of it. Okay. So that there is how you actually draw some contours. And that's working with bathymetric data from the SRTM30 dataset, which is freely available on the internet. And there's links on my website. So, that concludes our first exercise. The second exercise is to work with some satellite data. And we're going to be particularly focusing on Landsat, which has been made freely available now. Landsat is a US run operation that has been collecting data for a long time, and it takes essentially photographs of the world with around about 30 meter plus resolution. So it's not incredibly fine detail, but it's good enough to look at large scale patterns and what's going on. So if we have a look in catalogue, we navigate to the Landsat folder. You see that there's a folder called individual bands, and in it we've got 1, 2, 3, 4, 5, 6, 7 different TIFF layers, and then we've got some metadata which has been associated with it. GCP ground control points. We've got some version data, some pointers to help us identify the data. This is from the Landsat mission Satellite 5, and we obtained it in 2010. So what we're going to do here, we're just going to drag one of these individual bands into our new GIS, and we see it's just black and white. Let's add a couple more. Just black and white. This is because the B in the file name stands for band. And what we're going to do is we're going to construct a multi-band image. And we're going to do that using a particular tool within our toolbox. I'm just going to remove these layers from my view, and I'm going to go search. I'm going to go Composite Balance. That's a tool that's going to merge the individual Landsat bands into one image file that we'll be able to visualize by using a multi-band visualization known as RGB. So practically every photograph you've ever looked at comprises of 3 bands of information, the red, the green and the blue. That will all become clear shortly as we just run the Composite Balance tool. Our input rasters are of course all 7 Landsat bands. And I'm just going to hold down the shift key and select the bottom one to select all of them in order and click add. What you want to make sure is that your band 1, 2, 3, 4, 5, 6, 7 are all in order here. If not, if you've got a situation where 6 is below 7, you want to make sure that you move it up using these arrow buttons. Okay, vitally important that you have your band in the correct order. And then we're just going to give it an output raster name of somewhere where we can find it. I'm calling it a TIFF file extension yet again. If you look here, you can see some different file formats that you can save your data in. So I commonly use TIFF or SVGrid, my 2 grid types of choice, and click OK. Now this may take a few moments to run. So what I'll do as I wait, I'm just going to show you the importance of the bands. So as we scroll down, we're looking at this is our particular satellite that we got our data from. We have these 7 bands in our Landsat 5 data. So we've got band 1 is blue information, band 2 is green, band 3 is red, and there's the wavelength of light that the satellite camera was picking up. First we've got near infrared, short wave infrared, thermal, and then we've got another short wave infrared. So we can look at these data and visualize these by changing the bands that we can see in order to enhance the particular patterns that we want to initially find. So what we have here is the composite band, and we see it looks kind of blue. And the reasoning for that is because right now, band 1 should be blue, however, the computer has automatically assigned band 1 to the red colour. So we need to swap blue and red around in order to get a colour image. So we right click, properties, and then here we change our band number. So 3 is red, blue is number 1. Click OK. So now we've got green land, brown mountains. We zoom in onto Anglesey, and we can see fields, we can see some towns, we can see some sedimentary events within Red Wolf Bay, for example. However, if we change the bands around, for example, let's make the red band the near infrared, which is band 4, and see what happens. So we've got near infrared coming through now, and we can see some major changes. We can see some highlights down here, trees and vegetation. We can see fields and even stronger colorations standing out from amongst the towns and the cities that we can see in the area. So let's try something different. Let's try changing the red to thermal, which is band 6. And that's we're getting some thermal reflections coming through in the red channel. So it's really picking out the clouds. It's not quite great. We can see maybe the colder areas in the top of the peaks in the Snowdonia National Park. We've got some strange beaches coming through. I don't know what that is there. But we basically see you've got a lot of power with this freely available Landsat data. Not only colour, but you can also use it to pick out certain bands that might show you some interesting patterns. That is the power of Landsat data. Really, really strong, powerful system to use, freely available to download for pretty much any purpose you want. So that's working with satellite data. You can get data from different years. They're all georeferenced. You can compare and see how land use change has happened and what's happened over the years and so on. As well as, for example, you can pick out sedimentary events, maybe plankton blooms in the Irish Sea. And remember, Landsat data is global, not just around our area. So, the final activity that we're going to do today is just going to create a visualization that shows some species distribution data. And I'll explain what I want to show you to see. So right now, in my worksheet, there's a small example of the kind of visualization that I would like to see, which is this one here. So I'm using 2 layers. You've got the course data set from my 2008 paper in deep sea research, and then we've got underneath that a finer data set from my 2011 +1 paper that I published with John Gunner. We've also got some contours. We've also changed the symbology of our landmass to black. The contours are 2,000 meters. So I want to replicate this particular visualization, and I want you to have a go yourself at drawing that. So if you're going to have a go, press pause now. Okay, so I'm going to take you through how to do that particular visualization. It's actually rudimentary, rather simple. We're going to start in Catalog by building up our base map countries layer. So we've got this here. Our main area of focus is the Northeast Atlantic. So I'll just zoom into Northeast Atlantic. First thing I'm going to do, change that to a black fill color. I'm going to remove the outline. So we just got black. I'm now going to add in my 2 data layers from a species distribution dataset. So they're both in here, so we can turn on and off these different layers. Now this is just 0 to 1, this is 0 to 100. Both inherently the same, we're just going to change the bounds of what we're going to do for the visualization. So right click on a layer, properties, symbology classified, classify, and define interval 20 for the 2008 paper. The color ramp I'm going to use will be red to blue, and I'm just going to flip it so that hotter colors indicate higher levels of suitability, i.e. 80 to 100% habitat suitability for the species of coral that we're looking at. Click OK. So there's our first layer, is visualise. The next layer, we'll do the same. But this time, we're just going to change our classified ramp to defined interval, but this is going to be 0.2 instead of 20. And click OK. Again, change our colour ramp to the red to blue and flip it. Click OK. Okay, so now we've got our visualization is starting to form. The next step is to create 2000 meter contours. I'm just going to add in my node bathymetry. It's asking me if I wish to build pyramids. Yes, of course I do, because I want to be able to see it quickly. And there's my node data set. Remember, I'm going to use the contour tool to allow me to create my 2000 meter contour. meters. And there we go. One interactive visualization where we can turn off and on and predictive distribution models. The Rocker Bank, Hatton Bank area looks to be a bit of a hotspot. Porcupine Seabright, we've got some points down here. If I turn it off, compare that to the 2011 data, much higher resolution and lots more habitat predicted as suitable. That's it. Really simple, really quick and easy. Just using the different tools to create a strong visualization that allows us to figure out exactly what's happening. Those two papers are available to download from my website if you wish to know more about that particular data set. Thank you for listening.